Okay, we're going to learn how to turn register machines into predicate logic notation. So this is something you have to do for your homework, and I thought it'd be helpful if we went through an example and you had access to that to work on it. So I'm going to give you a register machine. This one is one where you go into register A and you add 1. You go into register B and you add 1. You go into register A and you subtract 1, and if you can, if it's not empty, you subtract 1 and go into register B. But if it is empty, you go down the empty arrow. Okay. Now, in order to translate, to turn these into predicate logic notation, it's helpful for us to have numbers, labels for our arrows. So this is going to be arrow 0, this one's going to be arrow 1, this one's going to be arrow 2, this one's going to be arrow 3, and this one's going to be arrow 4. And we're going to be using a predicate. In this case, it's going to be a 4-place predicate. The number of places in your predicate will always be 2 more than the number of registers in your register machine. And the different places in the predicate represent the following things in our intended interpretation. So this is going to be the time. The time starts at 0 and increases by 1 every time you perform an instruction. This is going to be the arrow number. This is going to be the number in A at a given time, and this is going to be the number in B at a given time. So, for example, there are ways that we could describe possible states of this machine, right? And we could decide whether these descriptions are true of them. So I'm going to write 0, 0, 2, 0, right? What that means is that at time 0, we're heading down instruction arrow 0 with 2 things in register A and no things in register B. And given our conventions about how we carry out computations with register machines, in fact, at the beginning, this is a true description of what's going on in this register machine. Here's another description of a possible state of such a machine, right? It could have 3, 1, 0, right? So this represents at time 3, we're heading down arrow 3 with 1 thing in register A and nothing in register B. Now, we can actually have a look ahead, and would this actually be a true description of some state of computation of this machine if we started this with 2 things in register A? So we'd go into register A. At this point, we're at time 1, and we've added something into register A. So there's 2 things there are 2 things in there to begin with, let's suppose. There are now 3 things. And then at the next time, there's now 1 thing in register B. And so that's at time 2. At time 3, there's going to be 2 things in register A. And we're going to we are going to be heading down. Well, actually, I'm not sure. So let's say this is time 1, this is time 2, this is time 3. So yeah, we are going to be heading down arrow 3, but we're not going to have 2 things in register A at this point, because we started with 2 things in register A, and we added 1 in earlier on, and now we've taken 1 out, so we're going to have 2 things in register A. And we're not going to have 0 things in register B, because we added 1 in, so there are now non-zero counters in register B. So this is not a true description of any state of this machine when we start this machine with 2 things in register A. So we could have, there could be true descriptions when you fill in these with names for numbers of counters and times, and there could be false descriptions of machines. Okay, but that's essentially what our predicate means. Okay, so if we want to give an account of, if we want to describe this machine in predicate logic, we have our predicate, and we want to now describe every possible transition for this machine in predicate logic. So one transition takes you from arrow 0 into A. You add one thing, and you come out in arrow 1. That's one transition. It's the first transition. So how would we describe that in predicate logic? Well, we're always going to have universal quantifiers. And we're going to start with, if we're in a state where we're at time x, we're heading down arrow 0. There are y things in A, and there are z things in B. Then, after performing this transition, we'll be in a state where the time is x plus 1. We're heading down arrow 1. We have y plus 1 things in register A, and we have z things in register B. Right? So this now says that for all x, for all y, for all z, if x is a time, y is the things that are in A, and z is the number of things in B, if we start at time x down arrow 0, we're going to, at x plus 1, be heading down arrow 1 with one more thing in A than we started with, and with whatever is in B before still in B. Okay. Now, the book actually asks you to describe the type of transition, and the type of transition for any transition indicates the arrow numbers, 0 to 1 in this case, and then the thing that you performed. Here we added 1. So here we have a complete description of one transition state of the machine. Okay, so okay, so there are several other transitions, right? If you think about it, let's write them all down. There's the one that goes down arrow 1. It'd be helpful if you could see the top picture as well, right? So there's the one that goes down arrow 1, goes into B, adds 1, and heads out on arrow 2. Right? So let's think of the other ones. There's the one that goes down arrow 2 into A, and if there's things in A, takes 1 out and heads down arrow 3. There's the one that goes down arrow 3 into B, adds 1, and heads out arrow 2. And there's finally one more. It's the one that goes down arrow 2 into A, and A's empty, so it heads down the 4th arrow. So those are all the transitions that are in this machine. So if we want to give a complete description of this machine in predicate logic, it would be enough to give a predicate logic description of each of these transitions. Okay, so what I'm going to do is I'm going to do this one. So we start with our universal quantifiers for all x, for all y, for all z. X is the time, so if we are starting at time x, we're going down arrow 1 with some number in A and some other number in B. Then at the next time, our x plus 1 will be heading down arrow 2 with the same number that we had before in A and an extra thing in B, right? So z plus 1 in B. And as before, if we're going to describe the type of this transition, it's a 1, 2 plus. Okay. I want to make a note of, in the book, we could do this all perfectly well using the successor function, and that's really the way, I guess, in some sense we should do, right? So this would be the successor of x, and this would be the successor of z, and this would be, 1 would be the successor of 0, and 2 would be the successor of 0, not OS, but SO, and 2 would be SSO, right? But I think it's a little easier to see how this works, but do know that, really we've got hidden function symbols here in our predicate logic expression, right? We're abbreviating some of these function symbols. Okay, all right, so now I'm going to do this one. This is a minus transition. So we're going to start with our predicate logic, our universal quantifiers. We've got for all x, for all y, for all z. And now we're at time x. We're heading down arrow 2. We're taking things out of a. So we're going to say, well, if you have y plus 1 in at time x and some number of things in b, then at the next time, right, x plus 1, you're heading down arrow 3, and now you've taken one out, so you end up with y in register A, and you end up with z in register B. And so your transition, again, is going to be your arrow to arrow, so that's 2 to 3, and your whatever you did, what function did you perform? You added. Okay, now this one is very like this one, right? So I'm not going to do that one. It will differ from that one simply in the arrow numbers, I think, right? So instead of going from 1 to 2, you're going from, in this case, 3 to 2. Right? So I'm going to do this one. This one's a different kind. Now, when you're going down one of these, performing this transition, the only time you ever go down your empty arrow is when you go into A, there are no things in A. So we know there's nothing. We know there are 0 counters in A. So we're not going to have 3 quantifiers now. We're only going to have the 2. We have for all x, and I'm going to say for all z. It doesn't really matter. We could have y or we could have z. I'm going to use z because for some reason, and you can guess why it is. All right, so if at time x, we're headed down arrow 2, and there's 0 things in A, and some number of things, that's a 2, not a z, some number of things in B, then at time x plus 1, we're heading down arrow 4, still with 0 in A, and still with whatever we had in B, right, z. And so this is going to be a transition. The time is going to be arrow 2 to arrow 4. Okay, so here we have a complete predicate logic description, if you've got any details for this one, of this register machine program. So now we've got a way of turning register machines into predicate logic descriptions. Tomorrow in class what we're going to show is how to turn register machines and the question of whether they halt or not when started with some number of counters in register A into arguments of predicate logic. Right? And it's going to turn out that these arguments are valid if and only if the machines they're associated with halt. And we're going to prove that, right? We're going to prove, once we've decided how to represent these guys as arguments, we'll show that those arguments are valid if and only if those register machine halts. And then if that's the case, knowing that there's no procedure for computing the halting function, we'll know that similarly there's no procedure for decidability of validity and consistency of sets of sentences in predicate logic. At least predicate logic where we've got these function symbols and these kinds of quantified sentences. And we'll talk about those kinds of details tomorrow. And of course, all of this is presupposing the truth of the Turing thesis. Because if tomorrow one of you comes up with a notion of computability that can compute the halting function, then all of this goes out the window. Presumably then we could find a procedure that would be decidable for predicate logic. But, if you do that, that would be great, but probably you wouldn't. Okay, so hopefully that helps you do your homework, and I think I'm signing off.